Okay, so this is going back a little bit in time, but let's just make sure that we're all on the same page about prediction intervals and what they're doing, and then we'll sort of walk through to make sure that along the way that you sort of are understanding what each of these different pieces are. So in addition to the prediction intervals that are predicting the confidence interval for a future response, we'll also talk about if you wanted a confidence interval for the mean response of a prediction rather than a future response. Okay, so this was an application exercise from a bit ago, and I asked you first to input the design matrix of X from the following data. And the reason I'm having you do that is I basically want you to I want you to sort of get an understanding of how indicator variables work, because these are really commonly found in statistics in general. So I'm going to create a little chunk here, and this is going to be called design matrix. And so if you recall a design matrix, of course, the first column is always going to be ones, and then the subsequent columns for indicator variables are going to be for each of the different indicators. And so if I look here at this data set, I've got a small data set with an outcome and an X variable or a predictor age. And there are 3 unique categories here. So the unique categories for age are less than 20, from 20 to 50, and then greater than 50. So there are 3 unique categories, which means that I need to create 2 indicator variables, with the third category being the referent. And so I can decide now what I want to be my referent category. For example, if I wanted my models to be fit such that both less than 20 and greater than 50 were compared to this 20 to 50 range, then I would have 20 to 50 be my referent category, so I would leave that one out of the model. Or similarly, if I wanted to compare everybody to the young folks or everybody to the old folks, then I would set those as my referent categories. So I'm going to pick less than 20 as my referent category, which means that I'm not going to create an indicator variable for less than 20, because it can be fully assumed if you have zeros in the columns for both 20 to 50 and greater than 50, because these are mutually exclusive, which is a necessary condition for a categorical variable, then we know that if they aren't in either of these categories, then they must be in that third one. Okay, so let's make this design matrix X. So it's going to be a matrix, and the first column is just going to be ones like we usually do. So I'm going to repeat. We've got 1, 2, 3, 4, 5, 6 is our sample size here. So I'm going to repeat 1 6 times. And so that's going to be my first column, my column of ones. And then my second column is going to be an indicator variable to indicate whether the observation is in group 20 to 50. And the reason I'm skipping less than 20 is because that's my referent category, so I'm not going to have a column for that. So this is going to call, well, I don't actually have to name it, I suppose, but I would call this, if this were in a data frame, I'd call this age 20 to 50. And so I look down here and I say, is this first observation between 20 and 50? They are not, so they're going to get a 0. Is the second observation between 20 and 50? Yes, they are, so they're going to get a 1. Is the third? No, they're not. They're going to get a 0. The fourth, a 0. The fifth, a 1, because that fifth observation is between 20 and 50. And the sixth is going to be 0. Okay, so that's my second column of my design matrix. And now I need one more column, an indicator for whether or not they're in this last group, greater than 50. So I'm going to do the same thing. Is this first observation greater than 50? No, so they get a 0. Is the second? No, so they get a 1. Is the third? Yep, so they get, so they get a 0. This 0, 0, and then they get a 1 for this third, because yes, they are. Is the fourth? No, so they get a 0. Is the fifth? Nope, so they get a 0. Is the sixth? Yes, so they get a 1. So as you can see from this design matrix, and let me just go ahead and run this. What I need to make sure I say I want there to be 3 columns. So let's take a peek at that. So we've got our first column of ones. Our second column here is our indicator for whether or not you are in the 20 to 50 age group. And our third column is an indicator for whether you're in the greater than 50 age group. And so just looking at this matrix, I can guess exactly, I don't even have to guess, I can know for sure for each observation what age group they're in, even though I only have a column for 2 of the 3 age categories. And that's because if they have zeros for both 20 to 50 and from greater than 50, then I know that they must be in the less than 20. That's my referent category. So for example, the first observation and the fourth observation are both in my less than 20 group, which of course aligns with what we see in our data set. Okay, so that answers the first question. That inputs the design matrix into R. And the next was we need to estimate beta coefficients for predicting Y from age. And so from that, I'm going to need to actually put in my Y variables. So I've got 2, 3, 5, 10, 1, 3. So I just pulled those from this data set. I can run that. And of course, if I want to calculate my beta coefficient, we know we've been doing this over and over. We know how to do that in R. It's just going to be the X transpose times X inverse. So that's what this does. This takes X, transposes it, multiplies it by X, and then takes the inverse of that whole thing. We multiply that by X transpose and multiply that by Y because that is our estimate for beta hat. And so when I run that, I get 6, -4, and -2. And so what do these values correspond to? Well, 6 is my estimate for beta 0, my intercept. And so I assume basically when, in this case, because we're dealing with an indicator variable, I assume that when my second and third columns here are 0, then we're going to end up with this beta 0 of 6. And so what that means, because we have just one categorical variable being modeled in this data set, that means that when the age is set to the referent category, so when age is less than 20, we estimate a Y value of 6. So the way that you interpret an intercept when you're dealing with indicator variables, because the interpretation of an intercept is when all of your beta coefficients or when all your X variables of your model are 0, then you'll zero out all of the other components of the model, and all you're left with is that slope or that intercept. And so in this case, we know that the other X variables are going to be 0 when we're dealing with our referent category, which in this case is age less than 20. And so we can interpret that coefficient actually becomes interpretable in a way that's actually useful. Sometimes the intercept isn't useful, especially if we're dealing with continuous measures where an X variable being equal to 0 is not really sensible. But in this case, because we're dealing with indicator variables, it's actually a very helpful measure because what this shows us is that when age is less than 20, we would expect the Y variable to be 6, so our outcome to be 6. And then this next value, this next beta coefficient, this is beta hat 1. So beta hat 1 here is -4. And because my X1 in my design matrix, if you remember, this X1 corresponds to an age category between 20 and 50. And so we would say being in the age group 20 to 50 compared to being in the age group less than 20, compared to our referent category, yields an expected Y of -4. So basically, if we moved from the less than 20 group into the 20 to 50 group, we would expect a change in Y of -4. And then finally, this last one, this beta hat 2, this corresponds to our third column here, which was for the greater than 50 age category. And so that would be when age is greater than 50 compared to age less than 20, we would expect our outcome to be -2. So that's how we interpret those. And so now we're going to do an example where we are actually fitting a model that has these indicator variables in it, and then we're also going to be calculating things like the variance as well as the prediction intervals. So we're interested in predicting a chicken's weight based on their diet using the chick weights data set. And so the first thing I need to do is fit the model of interest, and I need to extract the beta coefficients. So I'm going to do that here. So I'm going to fit this model. And so I'm going to use the LM function, and my model of interest here, I want to predict the weight from the diet. So let's take a look at what this chick weights data looks like to make sure we know how to use it. And so we've got here a column for weight and then a column for feed. So I'm going to just run this model quickly so we can see what it looks like. So I'm going to do weight tilde feed data equals chick weights. And what do I see? Well, because feed is a categorical variable and R is smart, it has created these indicator variables for me. And so I end up with 1, 2, 3, 4, 5 indicator variables, which means that there must be 6 levels to that feed variable. And I can see exactly what those levels are if I use the levels function. So I can do chick weights feed. And I see that these are the levels here: case-in, horse bean, linseed, meat meal, soybean, and sunflower. And so because this is the first level that's listed here, case-in, I know that that is what is being, that's the referent category. That's what all these are being compared to. So for example, if I wanted to interpret what this was, I would say that being fed horse beans compared to the case-in is yielding a change in weight of -163, an expected change in weight of -163. Or if I wanted to interpret the sunflower one, I would say the chickens that are fed sunflower compared to the case-in their expected weight is about 5 higher. Okay, so there's our model. If we want to extract those coefficients, there's a couple ways that we can do that, but I can use the coef function here like this, and that'll pull out the coefficients. And I'm going to actually, because I might need some other pieces of that model, I'm going to save the model, and then I'll extract the coefficients like this. Okay. And now I need to construct an x0 for a chicken that's eating sunflowers. Okay, so if this is going to be sort of akin to what we did up here, where we created an our entire design matrix, but instead of needing a whole design matrix, we just need one vector for this future prediction that we're trying to make. And so my x0 is going to have the first value will be 1, because that is that's the value for the intercept. That's going to be my value, so I can calculate what the intercept would be. And if I'm looking at all of this, is the order that I know my beta coefficients are in. And so if if this chicken is eating sunflower, then what would the value for feed be for horse bean? It would be 0. And what would their value be for linseed? 0. For meat meal, it would be 0. For soybean, it would be 0. And for sunflower, it would be 1. So that's my x0 there. That's my x0 for this particular predicted value that I'm trying to get, for this observation that I'm trying to get a prediction for. And now if I want to calculate the predicted weight for a chicken eating sunflowers, I can take that x0 and I could transpose it, and I can multiply it by those coefficients from the model. And so I end up with this 328, and so that indicates that a chicken eating sunflowers, we would expect their weight to be 328.9. Okay, so now I want to calculate the variance here, and these pieces here, this first part where I said show that the variance is equal to this value, I think we've already shown kind of how you can derive that. And we've also shown what the expected value and the variance is here of the predicted value. But let's see if we can actually code this up in R. And so if I wanted to actually calculate what the variability would be, if this was for a future observation, so if I was calculating a prediction interval for a future observation, then I would need to use this equation for variance down here, the 1 plus x0 transpose times x transpose x inverse, x0 times sigma squared. And we know this because we've derived this. You can double check those videos from last week to make sure that you understand how that derivation takes place. So let's actually calculate that. So I'm going to calculate that variance for the prediction interval. I'll call this variance pred. And I'm going to take 1 plus that x0. And now we need an x transpose x. And so let's see. Well, first we got to transpose this x0. But let's pull an x out here of this model. So there's a function called model.matrix. And if I do this model.matrix times the model, or of the model itself, it's going to pull out that design matrix that you would be creating. It's going to pull out that design matrix itself. So I'm going to do that. I'm going to say our x is equal to model.matrix of mod. So what this model.matrix is pulling the design matrix out of the model that we fit, the linear model that we fit up here. Okay, so now I need that design matrix because I'm going to multiply it. So I'm going to take, I take the inverse of x transpose x here. So I'm going to do solve of transpose of x times x. And then I'm going to multiply that by x0. So just to remind us what we're doing, we took 1 plus x transpose naught, that was that little vector that we created, times x transpose x inverse times x naught, and then we multiply that whole thing by sigma squared. And so how do we get the sigma out of this model? If you recall, we can use the summary function of the model, and then we can pull out the sigma, and then of course we'd have to square it. So we're going to multiply this by sigma squared. Okay, so let's see what that looks like. Okay, so that's the variance here of this future, if we were doing a future prediction for this prediction interval. And so what do we do with that variance? Well, if we want to actually create an interval for this, it's going to be that this is going to be the y hat, or the predicted value for x0. I'm going to call this y hat x0, just so we can remember what that is. It's that 328. That's the predicted value for a chicken that eats sunflowers. So if we found a future chicken and we wanted to know what its weight would be if it's eating sunflowers, then we could estimate that that weight's going to be 328.9. And if we wanted a confidence interval for that, we would take that y hat x0, and we would, if we wanted an upper bound, we would add. Now, what are we going to use here for our pivot? We're going to use a t star. So let's calculate that t star maybe up here just to do it separately. So we're going to use the qt function. And what are we going to plug in for p? Well, in this case, I'm going to plug in 0.975 because we want a 95% confidence interval. And then what are we going to plug in for our degrees of freedom? Well, what do we need to know for our degrees of freedom? We need to know some information about this model, and we also need to know information about the data set. And so how many predictors were in this model? We had 1, 2, 3, 4, 5, because we had 5 indicator variables. And so and how many variables were in this, or how many observations were in this data? Well, I can use the nrow function to check how many observations are in the chick weights data. It's 71. And so we know that our degrees of freedom are going to be n minus p plus 1. So this is going to be 1, 2, 3, 4, 5, plus 1 is 6. So n minus 6. So that's going to be our t star, which is 1.99. So I'm going to do t star times the square root of the variance of this prediction. And so that gives us an upper bound. And if we want a lower bound, then we'll do minus. And so if I look at these together, I would say that I'm estimating that a chicken that eats, a future chicken that I find out eats sunflowers, I estimate that it will have a weight of 328.9 with a prediction interval of 214.9 and 442.9. Now, what if I just wanted to know on average what the weight of a chicken that eats sunflowers is? So I'm not making a future prediction. I just want to know on average what we would expect that to be. Well, that y hat value, as we've talked about, is going to be exactly the same because we're still going to predict the same number. But the variance is going to be slightly different. And basically, it's just not going to have this 1 plus, because if we're making a prediction about the mean, we end up having a smaller confidence interval, which makes sense because it's easier to guess what an average value is going to be as opposed to guess what a specific future value is going to be. And so I'm just going to copy this, but now instead of doing this 1 plus, this is going to be the variance of the mean response. So I'm going to call this mean, and I took out that 1 plus here. And now I can get that variance as well to be able, and I can stick that into this confidence interval. And so now if I was trying to tell you that I would like to guess about the variance or about the average weight of a chicken who was eating sunflowers, I would tell you that my confidence interval for the average is going to be 297 to 360. And so that's slightly different here than my confidence interval for when I'm taking, look how much wider this is. If I'm taking my confidence interval for a future prediction, it goes from 214 to 442 versus my confidence interval for the average, it goes from 297 to 360. And so in both cases, my center of this confidence interval, my actual prediction is the same. I'm still predicting that on average, I think chickens that eat sunflower seeds have a weight of 328. And similarly, if I were to predict a future chicken, what the weight would be that eats sunflower seeds, I would say that I think that weight's going to be 328. But my certainty interval is going to be different. If you're asking me about the average, I'm going to give you a certainty interval from 297 to 360. If you're asking me about a specific future observation, I'm going to give you a confidence interval from 214 to 442.